Okay, I think we can start. We have actually some choices to, yeah. Oh, dzięki. There are three things we can do. I prepared two nice exercises. You can either start from the first one or from the second to build on, which is to build on top of it. And the first one is if you go to this, if you clone this repository, which is at the top, there is a small protocol that is doing streaming. It allows to stream a single file or a single something through a Unix socket. There is a small application that allows you to run it and stream a single file. And the first thing would be to extend it to allow to stream multiple files. So this is one simple exercise how to work with this protocol stuff. The second thing is to build on top of it, to build a pipelined client that allows to pipeline the streaming, so send multiple chunks of this file and then collect responses later. And third thing, which we can do either at start or if we have time at the end, we can try to build a small session type framework, which is very similar to that one, and see a little bit how this framework is built. So it's up to you to choose what you want, which part you would like me to start on.
I'd prefer to see how to make the sausage rather than how to eat it. So I'd go for the...
Okay, so who's for that option? Okay, so like 4 people. And for to work with a session type thing with a small protocol and to extend it. Can you raise who wants that? It's a clash. It's 4. So.
So you get to decide.
Okay. So we'll.
So
we'll start with this one, and if we'll have time, then we'll do that part. And for it's a thing that everybody can do on its own actually. And you can either start with the easier version, start with this protocol that is defined, and work toward streaming multiple things. Or there is a branch. If you look for branches here, there is a branch where this part is done, and you can start on top of it and explore how to do pipelining. And we have 2 hours today. In 2 hours, you'll probably be good enough for you to explore how to do that. Okay, so I'm running here the Linux subsystem on Windows, which I'm not very fond of. Yeah, font probably is here. Is it good enough? Big enough?
Yes.
Okay, so so there are you can build this thing with Cabal. So you'll need Cabal.
Could you change the colors to dark on white background?
Flip the colors.
Yeah.
Let's see if it will work. Okay, seems okay. Okay, I'll first maybe present what is the protocol. So the protocol description is in this type package, type module, source network protocol stream type. No, it's not working very well. Maybe let's find some other. Morning. That's slightly better, I think.
Still invisible. Still some things. Maybe those are spaces. Maybe those are actual spaces.
Yeah. I think everything is visible now. So this the protocol tag is called stream, and this will be this lifted type used as a kind. It's polymorphic in IDs and chunks, so how you identify your resource and what are the chunks that are coming through it. And it has 3 states. So there are 3 possible states. Either the system is in the idle, which will mean that the client will request a single resource identified by this ID thing. And in the busy state, we want the server respond with chunks of that resource, and when it's done, we want it will communicate the end of communication. And then we have a protocol instance where we have to define all the messages for in our protocol. So this has just 3 messages. This message get is to get a single resource. I added a size of a chunk that you can also decide on the client how big the chunk will be to get. And you pass this ID as well, so it will be probably a file path or something like that in our simple demo. And it transfers the state from idle to busy. And then we have another message that allows to send a single chunk. So it's a very simple wrapper. And it doesn't change, this message doesn't change the state. So sending a chunk leaves you at the same state. The server is still busy sending more chunks. And there is a message that allows you to communicate to the client that everything was transferred. So this is this message end stream. And another piece of information that we need to provide is this partition of states between client and server. That is disjoint. So these are these three data declarations. So client has an agency only in the idle state. So here you have this type stIdle of kind of kind stream. In the server has agency only in the busy state, and nobody has agency in the done state. So this is the partition between client server and the done state, whereas nobody has the agency. And this is the partition in the set theoretical sense, that you have a set of your states, and you want to have a disjoint, to present it as a disjoint sum of sets that are of states that are only belongs to the client, states that only belongs to the server, and the terminal states. In this protocol, we have only one terminal state, one state that belongs to the server, and one state that belongs to the client. And if that's the case, that you provided this partition, that it doesn't have any overlaps, then you can then you will be able to define this exclusion lemmas. And if this works this way, that here when you pattern match on this talk idle, the compiler will infer that there is that this shared state st, this state variable, must be in the must be equal to idle, and there's no constructor in this GADT that constructed. So you can pattern match on this constructor, and using the empty case, Haskell will be really happy to conclude that there are no such things. And this way, you construct this proof that there is no overlap between client and server states. And the same for the terminal states, that there is no overlap between terminal states and client states, and terminal state and server states. And yeah, that's actually what this model provides. There are two simple instances that allows to show messages or compare them, which might be useful for debugging or for running some tests. So the next step is how to model this protocol as a single data type, without actually speaking up in this type-safe fashion. It's actually quite useful to first try build something, some simple GADT that corresponds to this protocol. And if you go to the client module, there is this stream client GADT, and this is how you would actually do this kind of protocol without speaking at all in this type shape framework. So you would define a data type that allows you to do the request. So it provides this ID, the resource ID and chunk size, and then gives you a way to collect all the responses that are coming. And when you're collecting responses, you will either await for a next chunk to come, which means you want to consume a chunk and produce and have a way to still await for more chunks. So this way you can encode it as a function from chunk to getting another collect function. You might want to do some effects here on the boundary, so it might be useful to wrap it in a monad or functor, whatever. And another handler that you want to have, that you need to have, is for handling the end of stream response, which when the stream finishes, we're done with the computation, so we can return some value that maybe this client wants to compute out of this communication. And now if we have such a description of the protocol on the term level, we should be able to build an isomorphism between this stream client and a peer. So to embed this in this peer data type that I showed you. And here is how you would do that. So this stream client peer function takes a stream client, so this GADT that can request something. It has only a single constructor, this request ID and chunk, and the continuation, like collect, because it's this collect thing inside a monad. And we want to request something, so we want the yield constructor that we construct a request here. We know that we are in the idle state, so we use this client agent talk idle thing, and we pass the message. And now we need to have the continuation. Maybe it's actually useful to have type protocols, source, network, core, and there is this peer. Where is peer? Okay, so this is this yield constructor we're using here. We pass this this token here, the message, and now we want to pass also the continuation from the state that the message transforms us to. So here this message get changes the state from idle to busy. And in the busy state, it's not the client that is the agent anymore. It's the server that is the agent. And now we want to await for things coming from the server. We don't have access yet here to this collect thing that has the handlers, we need to unwrap it from the monadic context. So for that reason, here is this effect constructor of peer that allows you to unwrap the collect. And yeah, it's calling the continuation, which is called collect client peer, and it takes a collect, which allows to get a single chunk, and it constructs a peer from the busy state. So this is the state which we want to continue on, because the previous message that we sent brought us to this state. So here the only thing we can do actually is to await for a message. Here we pass the token that says that we are in the busy state, and awaiting means we pass a lambda that takes a message, and there are only two messages that we can get. Either the server will reply to us with a chunk, or it will reply to us that this is the end of the stream. So in the first case, we have a handler for each chunk. We call this handler. We have to use this effect thing because it is in a monadic context. And this handler was giving us back this collect thing. So, and also this message didn't change the state of the system. It changed the state from busy to busy. So we can still use this collect and still use this function that we're constructing here recursively. To get the next chunk, and the other message that we can get from the system, from the server, is the end of stream message, and this is different message because it changes the state from busy to done. So we can only finish the communication, so we can use this done constructor, where it's here, this done here, that allows you to just embed a single value. So we embed this handle and stream value that the client computed in a recursive way. So this is how you would construct a single client for this protocol. The second part is to construct a server. So what kind of handlers the server needs to have? It needs to handle the request, so we need to have a handler that takes this ID and integer, and then it has to be able to stream this resource. So it returns a producer, and this producer has two constructors. It can either produce a chunk and a continuation, or it produces an end of stream. And this is GADT representation of a server side of this protocol without type level assurance that they match. You can write an isomorphism from this type to the corresponding peer with this type here. So it's peer stream with as server starting in the idle state. And this function is also quite straightforward to construct, because you're at every step is, when you design properly the GADTs here, it's only one thing that you can actually do at each step. So first thing what the server will do will await for a request for a given resource. So we await for that. And there's only a single message that we can get. It's only message get that we can receive from the client. If we receive it, we do effect here, because our handle stream will give us the producer in a monadic context. So we call it and unwrap it from the monad and run the producer continuation, which now produces a peer that runs in the busy state, because the previous message transformed the state from idle to busy. And in each step here, we either have a producer that gives us a chunk, and when it gives us a chunk, we yield the chunk using the message chunk, and we pass this singleton that says that we're in the busy state, and we continue recursively. Or if we received an end of stream, we just unpack the value, send to the client that it's the last, that we already sent the last chunk, and we terminate the protocol at the server side. Now, there are two ways of testing, or two levels how you can test this setup. First one is provided by the library, and there is a module which is called protocols network proofs, and there is connect function, which has really nice type signature. It takes a peer, this is this first argument, where this first parameter to peer is just a protocol tag. The second parameter, PR, is this agency thing, is either client or a server. Not an agency thing, but a tag, whether this is a client or a server, one of those. And as any state that it starts from. Oh, it's here actually. And the second peer has everything the same, but the agency is flipped. So if we pass a client here, the other will be server, or if the first one was a server, the other will be client. And given these two peers, you can compute this this value that they lead to, this A and B, that are at the final state of the protocol. It also gives back some a token which basically says in which state it terminated. But it's less important. It's much more important that we are able to construct a total function that takes these two pairs. And this definition of this function is also quite straightforward. All the complexity is hidden in the framework, like how to define the framework so that you can get this kind of behavior at the output. It's probably good to go through this function. So all the logic is in this Go continuation. If both client and the server, let's say that the first is the client, the second is the server, are in the done state, so we reach the bottom, we just return the values and the state in which they finished. If one of them is the effect, we just unwrap the effect and continue. So there's nothing there. If one is yield and the other is await, then we know what to do, because we just pass the message from the message that one yield to the other. So if the first yield a message, the other is awaiting for it. So we pass it to this B continuation, and then we can just continue our computation until we reach the done. And without this type level information, you would be only able to do this and finish the function here, and you would be left with a partial function. And what all the type level machinery is for is to prove that you're not able to do anything else here. And in this presentation, we use this exclusion lemmas. For example, if the first one is quite nice. If two clients try to send a message being in the same state, something went wrong. It shouldn't be possible. So for that we have this exclusion lemma that because to yield a message both has to have the agency, and in your protocol definition you had to define this exclusion lemma to be able to construct a void, and that's how you can use the void. So you construct a you can use absurd to disprove that this is not possible. And the same in all the other cases, that if both sides are awaiting for a message, you can disprove it using this client and server has an agency lemma. So this is very useful. This function is useful for testing at the peer level. You have a pure computation that where you take both peers, you connect them directly against each other without any network sockets and whatever, and you can try in your tests if your logic is right or wrong. You can also do that at the level of these GADTs that we constructed without a peer. So when we have this client definition, and the server, they also should be dual to each other. So whenever a client requests something, this stream server type has to await for it. And it's how we did it. So we should be able to do exactly the same without this framework. And there is direct model, which does exactly that. It takes a client, stream server, and connects them directly. So this is another level of testing that you can do in this setup. Test your JDTs if they are well defined. Also working separately with JDTs and defining things separately from using the peers make it much easier to build an application, let's say, by another team or by other people that do not need to know this exact details how the framework works. They just need to define this, provide terms for these data types, and run it through an interface that you provide. Okay, there are also example implementations of a client and a server. So there is this very simple stream client that takes an ID, takes an integer, and constructs a request, and then collects all the responses. The same for the server. I use the pipes package here. If you provide a pipe that is producing chunks, you can construct a stream server out of it. And how to do that? So you take this pipe that is producing chunks, you call the next method that the pipes package provides, and you either this produces gave you the next chunk, which is the right constructor. So you get the chunk and the producer of further chunks, and you can construct the streams producer with this chunk constructor, or you will receive the final thing. So the producer was exhausted and left you with a final A value. So you end the stream here. And working with streaming libraries makes slightly more difficult to do resource handling, because you're not in a single monadic context. You're constructing a JDT that will guide how the application will go through. So handling resources is something that probably needs to be done at a different layer. As this is a really very non-productive example of how to do that. But it's useful for us to have one, because we will want to stream a file through this protocol. So I provided this with a resource function that that takes as an input a way of opening the resource and a way of closing it, so like a handle, file handle or something like that, and changes the type of this identifier that it's dealing with, because you will want to deal with either files or handles, file handles. So when the server starts and receives a request, we open the we open the resource, goes through all the procedure, and end the resource at the end. It's not exception safe at all, and it's meant to be like that for this presentation, for the sake of simplicity. Okay, there is a demo in the demo stream directory. Where is the main function? Oh. So it reads the arguments, and then if you type client or a server, there it will start either a client or a server. So let's see what's first. What is the client? So it works over Unix sockets. It's a very simple socket application, and it connects to default address, which is not configurable here. The framework provides this run peer function for you. It's in typed protocols. Run peer. So this run peer function is a way of running peer over some channel, and you can construct channels out of Unix sockets or some other beer type thing. It allows just to read and write to it. You need to provide a codec, which I will skip that part for a second. We use Seaborg Seaborg library for encoding data to byte strings, and the peer, and you run the peer against the channel, which interprets the awaits as reading bytes from the channel, and yields as writing things to the channel. So it's nothing magic here. And the peer we're running here is this stream client that we construct. We first call this client map that construct this GADT, and then interpret it as a peer with the stream client peer function. And the file server, it's just as we're used to, like to socket server programming. We bind to a socket, we listen on it. There's very simple accept loop with also no exception handling at all. And on each accepted connection, we run a peer. We construct a channel for this socket that we receive. And the peer that we're running here is this stream server from pipe. So the pipes library, pipes package there's a pipes bytestring package on Hackage, and it provides a producer that takes file paths and gives you a producer that will produce chunks of this file of a given size, so you can predefine the size. And this is where the size, the chunk size from the client lands here at the end, and this function will take each chunk of this file, stream it through this peer, and we use this with resource thing to open and close the file. I'm sure we can run it. You run demo stream, I think it was called. Okay, so we need some file. Maybe it's good to write one. I have one, so I think it's good enough to stream. So this is server, so we just run the server, so it's running, and now the client. Maybe it's possible to put this side by side. Where is this cursor? Okay. Cabal neuron demo stream. Client, let's say 10. Yeah, did work. So we asked to stream this temp/x file and to take 10 characters at a time. So we took each line and stream it, and the client sent the request and received all the chunks and received the final stream. Okay, so we're so this is how the streaming protocol looks like. So the exercise first is to extend this protocol to be able to stream multiple files, not just a single one.
You mean multiple files sequentially, one file?
Yes.
First, then
the next one. So we need to modify the protocol for that.
But I guess all the files that I want to have streamed to me in a single request, right? do I go back to a state where I await yet another request for yet another file and just simply have a session that is longer?
Yeah,
The
exactly.
second one.
Yeah.
Okay.
Do we do a break now, or what's the?
I think we're supposed
Oh
to.
yeah, it is time. It's the back.